Yeah, I'll start and say we're very happy to have Hossein speaking to us in the series. So he's a PhD student at NYU, and this talk is going to be on some things that are related to key transparency, which is an area that a bunch of us in the cryptography group here have been working on a lot. So we're very excited to hear the latest.
Yeah, thanks for having me. Let me know when I can begin.
Yeah, so take it away.
Thank you. So yeah, today I'm going to present IronDict, transparent dictionaries from polynomial commitment schemes. This is joint work with Alireza and my advisors, Benedict and Joe. By the way, I hope you guys have seen Game of Thrones. I'm going to be using some of the pictures and the references. The name IronDict is actually sprung from Iron Throne. So I want to start a talk by illustration of a very simple scenario in secure messaging. So imagine Jon Snow wants to text Ygritte on WhatsApp, and Jon Snow has Ygritte's mobile phone. So what he needs first to do is request public key of Ygritte from the WhatsApp server. But the server might be actually faulty, and in that case, it may actually return public key of someone else, like Joffrey. So here, Jon Snow has no way of knowing that it's actually texting the right person, and no way to find out about it. And it may end up in some awkward situations for Jon Snow. We don't want that happening. So this is where the transparency comes into play. So the whole goal of transparency is that everyone gets the same view of the server state. And since the server has to reply back consistently with the state, it means that the responses are going to be consistent for everyone. And the way it's going to solve the issue I illustrated in the previous slide is that so Ygritte herself can check that the public key on the WhatsApp server is correct. And now this time when Jon Snow queries to the WhatsApp server, since we have transparency and that their queries are going to be consistent, it means he's going to get the right public key this time. Otherwise, Ygritte will find out about it. And in a high level, the transparency model looks something like this. So we have the servers and clients as before, but we have two extra roles, the public bulletin board and the auditors, where like in a high level, the server publishes a summary of his actions, for example, commitments to different states of the dictionary on the public bulletin board. And some parties who are called the auditors will observe the bulletin board and audit the server actions. And if the server is being faulty, they have some whistleblowing procedure that would let others know about it, which might have reputational or legal consequences for the server. Now I want to talk about transparent dictionary, which is the abstract model we want to work with. So we can think of a transparent dictionary as a dynamic dictionary mapping a set of labels to a set of values, where the dictionary can have different states in different epochs. And what I mean by epoch is basically different discrete points in time. And it's a generic concept which can have like different applications in different settings. So the two most famous applications are public key directory and software distribution. So in case of the public key directory, the dictionary will be a mapping from usernames to the public keys. Concretely, in the case of WhatsApp, a mapping from phone numbers to public keys. And it has been already deployed by Keybase, WhatsApp, and iMessage. And in case of software distribution, it will be basically a mapping from the software version to the hash of the software. So when you download the software, you basically also want to get the correct hash as well, so you can hash the software and know you have the right software version. And it has been deployed by the Linux Foundation. But the application we are really interested in this paper and this talk is the public key directory. First of all, because working with public key directories, we have dictionaries which are larger than other applications. They can be, for example, as large as 2 billion, which was the number of WhatsApp users reported back in 2020. And we basically require higher throughput than other application, something like 200 updates per second. Basically, we just need like higher scalability than other applications. And we may have like extra requirements such as privacy, which may not be important for software distribution, where like all the information is public. I will illustrate on privacy later, by the way. But for now, what is the high recipe of building a transparent dictionary? So at each epoch, the server basically publishes a commitment to the current state of the dictionary plus some invariance proof, where the invariance proof basically proves that some invariance holds between consecutive epochs. I will also illustrate what this invariance proof is concretely later, but in a high level for now, at every epoch, the server basically publishes a commitment to the dictionary and some auxiliary data, which we call the invariance proof. Next, what are expected functionalities from a transparent dictionary? So the most obvious one would be probably the lookup operation, where we want to look up some value corresponding to some label at some state of the dictionary. For example, John Stowe might be interested in egress latest public key. But the other functionality, which may be less intuitive, is proof of consistency, which basically proves that value corresponding to some label hasn't changed from some epoch I to epoch J. For example, John Stowe might be interested in a proof that his public key hasn't changed since last year. But you may ask, like, why, for example, John Snow want to know his public key hasn't changed from some epoch I to epoch J. So assume that Jon Snow is beyond the wall with no internet connection from state I+1 to state J-1. He's been like offline. And the way that the server can cheat, which we call the ghost key attack, is while he's offline, the server basically replaces his public key with a malicious one, which impersonates him. And then before him coming back offline, reverse it back to the original. So when he comes back offline, he has no way of knowing that his public key has been tampered if he doesn't check those intermediate epochs or doesn't have like some sort of proof of consistency functionality. Okay, now let's see like what are essentially the proof of consistency is the challenging functionality. So let's see what are some different solutions to value consistency in existing work. So the most obvious solution is naive value consistency, where we want to check some value hasn't changed in state I+1, all the way to state J, where we can basically do the lookup operation for each of these states separately, retrieve all these values and check the equality. But the downside with this approach is that it requires J minus I proofs, which is expensive both for the server and client. And given that if, for example, if you're offline for 3 months, and currently WhatsApp has epochs every almost a minute on average, that's going to be like so many epochs and so many proofs that it's very expensive for the client. The other solution is version invariant. So in this setting, the server sets a version for each value in the dictionary, and initially the server for each value is 0. Now, each time that the value is updated, the server increments its version, and the server promises to increment versions if and only if the value changes. And assuming we have this version setting in place, the proof of consistency basically becomes 2 version lookups. If, for example, you want to check that some value hasn't changed from some epoch to epoch I to epoch J, you can basically look up the value at epoch, the version of the value at epoch I and the version of the value at epoch J, and check the versions to be equal. Because, for example, if the server has changed the key in those intermediate epochs and then reverted back to the original, it means that the version has to be incremented at least by 1. So the really cool thing about the version invariant is that it reduces like a linear number of lookups to only 2 version lookups. But the question is, like I said, that the server promises to actually increment the versions only when the value changes. But the question is like how to actually make sure that the server is honest and would act honestly. And this is where the proof of invariance comes into play. So you remember I said like at every epoch, the server publishes a commitment to the dictionary plus some auxiliary data, which we call the invariance proof. And here the invariance proof for the version invariant will be basically saying like a proof that versions are incremented only for the change values. For example, if you have a very simple dictionary consisting of only 3 entries, since only the first entry has been modified in this epoch, it means that the version for the first entry should be incremented by 1, and the rest of the versions shouldn't be touched. And this is what the proof of invariance would basically prove for us here. Okay, so far I have mentioned like what a transparent dictionary is. We know it's like a cool primitive. It has been already deployed by big companies. We know what functionalities we expect from it. But the question is like, so what are the research questions here for us, given that it has been already deployed by big companies? So going back to this diagram, I said we had the server and the clients, and there are some parties which we call the auditors, which are observing the server actions and audit the server. So the question is like, who are these auditors? And to answer that question, we basically should see what computational characteristic we actually expect from them. So their job is basically to audit the invariance proof. And it means that if the invariance proof is costly, the auditors have to be big servers because we expect a lot of computation from them. And if the invariance proof is cheap, it means that the auditors can be weak devices such as mobile phones and laptops too. And yeah, everyone can be auditors in that case. So to answer the question of like who the auditors are, let's see how expensive the invariance proofs are to verify. So as it turns out, audit proofs in Merkle trees, which are the baseline for almost all the deployments in practice, are really large. That's because proofs are basically linear in the number of updates per epoch. And giving you like some concrete numbers, it's almost equivalent to hashing 200 megabytes every 5 minutes to audit WhatsApp key transparency, which is too large for everyday users with weak devices like mobile phones. And as it turns out, basically the auditing job has been delegated to nonprofit companies such as Cloudflare, and we trust those big companies doing the auditing on our behalf. So billions of users are basically trusting like a few companies doing the auditing on their behalf. So one possible solution is that like we have some big proof and we want to make it a sing-sing proof. So one always general solution is like just throw a zk snark at it and make it have a sing-sing proof. And this is what we have tried to do in Hackathon. So Hackathon is a distributed snark which runs on a cluster of 4,000 machines. But even with like 4,000 machines, we only got a throughput of 10 updates per second. And that's because SHA and like all these other standard hash functions are very expensive to be implemented in the circuit. And obviously 10 updates per second is not enough, given that I said we need at least like 200 updates per second for WhatsApp key transparency. So our question here is that, can we make auditing cheap enough so everyday users with mobile phones and weak devices can do the auditing themselves and basically get rid of these third nonprofit companies? And the other observation is that Merkle trees do not give us perfect privacy. And privacy is really crucial for transparent dictionaries when they use in the context of secure messaging. For example, something like pattern of changing keys might be sensitive information. For example, if an adversary learns that I don't change my key very regularly, it may make me a potential target for them. As it turns out, tree constructions do not give us perfect privacy, and they always leak some amount of information, which they formalize via a leak function. So this leak function is not a standard function; it's just inherit from the construction, which they basically say like, oh, we only they define the leak function formally, and they say like, oh, we only leak this amount of information. And concretely, Seamless, which is the backbone of WhatsApp key transparency, each lookup reveals the last time that a key was updated. So the other question is like, can we have perfect privacy? And the answer is affirmative, and our solution is IronDict. By the way, thanks to OpenAI and ChatGPT for such amazing slide. This is my favorite slide. So our goal in IronDict is like, first, we don't want to have high server costs because we want it to be practical for large scales of billions, to be practical for secure messaging apps. We don't want to have high auditing costs. We want the auditing to be cheap enough so weak devices can do that as well. And we don't want any leak function. We want to have perfect privacy. And our solution is IronDict. But before getting into the paper, any questions so far?
One question about.
Yeah, please.
About the snark in Hackathon.
Yeah.
Did you try it also with a zk-friendly hash function?
Yes, we actually did with Poseidon, and so we get like 1,000 updates per second, but that's like a trade-off where like, are big companies, okay changing the Sarnet function into something like Poseidon, which is not standard?
Thanks.
Yeah. Okay, let's get into the paper. So a summary of our contributions. As our first contribution, we built a generic construction of a transparent dictionary based on any polynomial commitment scheme. Our scheme has perfect privacy, and we are the first scheme ever to have perfect privacy. We do have efficient support of fast forwarding, and our fast forwarding is 1,000 times better than Versa, which is the previous state of the art. And if you don't know what fast forwarding is, I will explain when we get to its slide. And the summary of the last bullet point is like our scheme is like highly practical. So for a dictionary of size 1 billion, we have self-auditing because our proof sizes are less than 10 kilobytes per epoch, independent of the number of updates, and they can be verified in less than 125 milliseconds. We have efficient lookup and proof of consistency, both for the server and client. We can support more than 1,000 updates per second. And finally, we have low memory and computation overhead for the server. So overall, the solution is like highly practical. But before getting into the paper, I just want to quickly review some backgrounds. So one technical term I'm going to be using is a multilinear polynomial. It's a multivariate polynomial where the degree of each variable is at most 1. For example, consider this polynomial f, which is defined on variables x1, x2, and x3. If you take a look at each term in the summation, basically the degree of each xi's is at most 1, and that's why it's a multilinear polynomial. And there is a famous lemma which says like evaluations of the polynomial over the Boolean hypercube is essentially a representation of the polynomial. And when we want to work with polynomials, we work with their evaluations over the Boolean hypercube. And the second thing is a polynomial commitment scheme, a PCS. So before saying what it is, I just want to say this is the backbone of SNARKs, which has been so much research on it for the past 15 years. It's just a standard primitive. And what a PCS does is it basically allows someone to commit to a polynomial f and later prove its evaluation point at some point x0 without revealing the whole polynomial with some cool properties. For example, we may have sync-syngness, which says that the commitment is small. It might be constant size and much smaller than the original polynomial. We can have efficiency. For example, the verifier time can be sublinear in terms of the original polynomial size. And finally, binding, where it says like the prover cannot change a polynomial once it has committed to it, as with all standard commitment schemes. Okay, now let's get into the paper. So our first step is like how to model dictionaries with polynomials. So as the first step, consider this very specific type of dictionary, which is a mapping from points on the Boolean hypercube to non-zero field elements for some finite field f. It turns out like there is a very clean and straightforward one-to-one mapping from the specific type of dictionary to multilinear polynomials, where like we can define its corresponding polynomial as it follows, where like the polynomial evaluated at point Li is equal to Vi, and for the rest of the Boolean hypercube is basically 0. And you can verify there is a very clean one-to-one mapping from that specific class of dictionaries and multilinear polynomials, which is great. But it turns out like we are interested in dictionaries from arbitrary strings to arbitrary strings, not that very specific type of dictionary. So next we're going to try to go from that specific type of dictionary to these general dictionaries. The first observation is that given a hash function which is collision resistant in one way like h, it gives us a one-to-one mapping from non-zero field elements to arbitrary strings, basically by hashing the string into the field, as long as the size of the field is larger than some bound, for example 2 to the 128, which prevents birthday attacks on the hash function. So it means that the specific type of dictionary I mentioned, which was from Boolean points on the Boolean hypercube to non-zero field elements, is equivalent to a dictionary from points from the Boolean hypercube to arbitrary strings. So we're one step closer. The range is arbitrary strings now, but we still have the domain to be points on the Boolean hypercube, which we need to get rid of it. And it turns out like the same strategy doesn't work again. So if we define a similar hash function from arbitrary strings to points on a Boolean hypercube, this is not going to be one to one this time. And the reason for that is like the size of the Boolean hypercube is more or less equal to the size of our dictionary. So even if we use a dictionary of size 100 billion, that's not still big enough, and you can do birthday attacks on it. So this hash function is not going to be one-to-one, and we cannot apply the same strategy. And our alternative strategy is like we keep two different polynomials. So we keep two different polynomials called index and value, where basically the index polynomial is a mapping from arbitrary strings to the points on a Boolean hypercube, and the value dictionary would be a mapping from points on the Boolean hypercube to arbitrary strings. So if you compose them together, it would give you like a general dictionary. So the high-level description of our dictionary will be something like this. At every state of the dictionary, it would consist of two subdictionaries, the index and value. And when you want to retrieve label corresponding to some label L, you basically have to look up the index dictionary first, and then you get some index Y, which is a point on the Boolean hypercube. And then you open the second dictionary at point Y, and you retrieve the final value, which is the value corresponding to your label.
So sorry, is that the big N there? That's the number of entries in the dictionary? Is that what that is?
N is like the capacity of the dictionary.
Yeah, okay.
Yeah.
Interesting. Thanks.
So next, what do we want from these dictionaries? So what are the expectations? So for the index dictionary, which is a mapping from labels to assign indices, we basically want it to be append only, but for the purpose of this talk, because I wanted to keep it math free, I don't want to say how we keep it append only, but it's like very simple. It's just a zero check, if you know what a zero check is, and the zero check is like translated into a sum check and some polynomial evaluations. So it's very simple, but I wanted to keep it math free. And the value dictionary, which is a mapping from indices to values, we basically don't have any constraints on it because the dictionary values can change arbitrarily. But one thing I want to say about the index dictionary is like, how do we assign indices to labels? So I said we cannot use one single hash function to assign indices to all the labels because we're going to get collisions. So our solution would be to apply open addressing. Open addressing in a high level is like when we iteratively use a hash function until we find some vacant spot in our data structure when we want to insert a new element. So our open addressing techniques works like something like this. Assume we have some hash function h, fancy h, which is a hash function from arbitrary strings to the points on the Boolean hypercube. And then we first like append 0 to the label, we hash it, we get some point, some point in the Boolean hypercube, and we basically check that the index dictionary at that point is vacant. If not, we this time hash 1 appended to the label, and then we get another point, and then check the index dictionary to be vacant or not. And we repeat this process until we find some vacant spot in the dictionary, and then insert the label at that point. One quick note about it is that like whenever we use open addressing, we basically need to use over provisioning, because and over provisioning means like the capacity of the dictionary is larger than the expected number of elements, because as the capacity of the dictionary reaches the elements, as you insert like elements, you basically have to do like a larger number of hashes until you find a vacant spot. And for that, we use over provisioning. And for example, if you use a over provisioning of 4x, it only takes us like 1.3 points until we find an empty spot on average, which is good enough. And the value dictionary, so I mentioned like we don't really have any constraints on it, so the server can update it as it wishes, but the value dictionary is important for proof of consistency. And to remind you, proof of consistency is when we want to prove some value hasn't changed from some epoch I to epoch j.
So just a quick question on the index dictionary, like how does that not, with this open addressing thing, how does that not allow the server to, I don't know, maybe we're going to come back to this, but to cheat, right? Like, so can he not ignore or pretend that the entry there before was corresponding to this, value L?
So you're saying like how we can have like two different indices for two different users, right?
Yeah, it seems like it like you're saying the hash function will like when you hash it with 0 might point two users to the same spot, but you're
Yes.
gonna have one of them is gonna be sort of bumped to another spot. So, but why can't the server cheat and say both of those users? Like only reveal pretend that and it was empty to begin with or something like that.
Yeah, so you cannot pretend it's empty. So if it's empty, it means like it's either 0, and if it's already taken, it means that it has to be non-zero. And when it's non-zero, you basically check what value it has. See,
So
like in the
I
last
can
line, we
see.
have set index of y3 to be hash of the label L. And that's like a real, hash from like arbitrary strings to the whole finite field. So that doesn't have collisions.
I see. Interesting. Cool. Thanks.
You're welcome. So yes, proof of consistency. So our very high-level idea for proof of consistency, which is very simple, is that we define these delta polynomials, which are difference polynomials for consecutive value polynomials. And we see that the difference of like value polynomial at epoch n and epoch m can be basically written as a summation of all these delta polynomials. And the observation is that if the value dictionary at those two epochs at some point x are equal, and a ghost key attack has taken place, it means that those delta polynomials were not all 0 and some of them cancel out each other. So our high level idea is that we basically use randomness so they cannot cancel out each other. So the result will be non-zero. And for that, we define these polynomials rand polynomials, where like rand n is going to be basically a random linear combination of all the difference polynomials. And the key observation is that if the rand polynomials at two epochs at some point are equal, it means that all the value polynomials for those epochs and the intermediate epochs were equal with a high probability. And if you're curious where the randomness comes from, so the randomness can be derived from the Fiat-Shamir heuristic. But you can also get randomness from other sources as well. If you don't trust Fiat-Shamir, you can, for example, get it from a random beacon. But the Fiat-Shamir is secure in the random oracle. So our model would be like this. Now we add the rand dictionary to it. So each dictionary state would be an index dictionary, a value dictionary, and a rand dictionary. So the index dictionary would be a mapping from usernames to the points on the Boolean hypercube. The value dictionary would be a mapping from points to the Boolean hypercube to the, for example, public keys or values. And finally, the rand dictionary would be a mapping from points on a Boolean hypercube to a random combination of the values, where we use it for proof of consistency.
One more question, sorry. Is the rand dictionary something you actually commit to, or is that just something you can like recompute? Like if it's Fiat-Shamir or something, is it something you can recompute on the fly when you need to generate or verify proofs?
No, we actually, so it's like more efficient if you keep it.
If you commit to it, you mean?
Like the commitment can be computed super fast with homomorphism, but you're basically like, it's better like to keep the actual transparent, the actual dictionary for the rand, in your database, because you can like, get it like fast on fly.
But security-wise, it doesn't matter. So
No, security-wise, it doesn't matter. It's just about efficiency.
thanks.
Yes, and so the next thing is like privacy in transparent dictionaries. So I said like privacy is very important in the transparent dictionary, and in a very high level, we define privacy for IronDict like this. So we see that server only reveals 3 types of information: some check proofs, polynomial commitments, and polynomial openings. And the key is that if we make all of these components zero knowledge, it means that all of them reveal only what they're supposed to. And each query basically only reveals what it is supposed to and nothing beyond that. And that's how we get perfect privacy. And also the same is also true about Merkle trees. For example, in a Merkle tree model, you have the commitment, which is the Merkle root, and Merkle openings. But the problem with Merkle opening is that you cannot make it zero knowledge because of the lack of the algebraic construction. But yeah, in our model, since we use an algebraic polynomial commitment scheme, it's easier for us to make it zero knowledge and hence get perfect privacy. And finally, concrete instantiation. So I mentioned like IronDict can be initiated with any polynomial commitment scheme, but what polynomial commitment scheme we want to go with? So we decided to go with KZH. So KZH is a recent polynomial commitment scheme, which is very similar to KZG. But the good thing about KZH that we decided to go with it is that it first has sublinear opening time, and very importantly, it has free opening for Boolean points, because most of the time the server is just opening like Boolean points for client queries. And for KZH, those are for free, which is very important. And second, it has efficient support of ZK transformation. So even for a dictionary of like, 1 billion, with only like 1,000 group operations, you can make polynomial opening ZK, which is like crazy efficient. And finally, KZH has constant commitment size, which is just a single group element. And we care about it because that has to go on the bulletin board. And it's like homomorphic and, has some other good features as well. And finally, implementation. So we have implemented our scheme for a dictionary of size 1 billion. And here's like a comparison from ZK IronDict initiated with KZHK to WhatsApp, which is based on seamless parakeet. So our lookup proof time for the client is the lookup proof size, and the lookup proof time for the verifier is like almost 20 kilobytes, which can be verified in like 30 milliseconds, while for WhatsApp is like much less. It's like 2 to 4 kilobytes, which can be verified in less than 1 millisecond. And basically the reason for that is like our CPUs are more hash friendly, and they're not really pairing operation friendly. The lookup time for the server for us is like 33 milliseconds, while for WhatsApp is 1 millisecond. By the way, we are working on some optimizations, which we believe we can also make the lookup time for the server to almost 1 millisecond as well, but currently it's like 33. And this was for an equal throughput of 100 updates per second. But finally, our audit proof size is only 8 kilobytes, which is independent of the number of updates and can be verified in 135 milliseconds. That number has to be updated. But for WhatsApp, it was like more than a gigabyte, which takes like 11 seconds on a laptop. So in terms of like the audit proof and verification time, there is no comparison. IronDict has much smaller proofs. And finally, fast forwarding. So I just want to quickly say what fast forwarding is. So assume you're an auditor, you have been offline for 1,000 epochs, and now you have to check 1,000 proofs. So the goal of fast forwarding is like you check less proofs. Or even like the extreme scenario is like you're a new auditor, you've joined the system, and now you have to check all the proofs since 2024, which was the start of the key transparency. Well, we don't want that happening. So fast forwarding is basically a solution that you check less proofs. And there are like two existing solutions for that in previous work and in our work. So one is like based on recursive snarks like IVC. So we do support a solution based on IVC with KZH, and our solution is like 1,000 times better than Versa for the server, because our circuit size is like much smaller, and for some technical reasons we can use elliptic curves, which are like 10x more efficient than the elliptic curve that Versa had to use. And the other solution is checkpoints, which basically reduces a linear number of audit proofs only to a logarithmic number of them. And we also support that as well, similar to Versa. And thank you.